So as we go through the topic of stoichiometry, one of the most important reactions that comes up all the time in the exam is combustion. And it's really one of the most important reactions in the world. Our entire modern world is based upon it. We use combustion to create electricity, and we also use combustion to create motion, and we use combustion to keep us warm. Combustion is the reaction of things with oxygen, and during that time when things react with oxygen, they tend to be releasing a lot of heat. So it's very exothermic reactions. And that heat can be used directly to warm buildings, or it can be used to spin things, which can create electricity or can create actual motion. So like if you're burning coal as your fuel source and you're combusting it, the heat from the coal burning is used to create steam, which causes turbines to rotate, which creates electricity. Or you can take a fuel and you can get it to be vapor inside of a motor. And as the vapor gets compressed with air, a spark can ignite the vapor, which causes essentially a mini explosion inside the chamber of the piston. And that very hot gas then pushes the piston down, causing it to expand. And as it does so, you can see that the piston going down cranks around this little rotating part at the bottom. This is called a crankshaft, and this is how a motor works to move your car. As the fuel is ignited, it pushes a piston, which causes something to rotate, and so that's how you can turn this chemical energy into the energy of motion. So in complete combustion, you're doing a specific kind of oxidation reaction where you're reacting something with oxygen. And for most combustion, we are dealing with something containing carbon. And so when you completely combust something containing carbon, all of the carbon atoms will end up as carbon dioxide molecules. That's the fully oxidized form of carbon in a +4 oxidation state. However, a lot of the time when we just burn something, we end up doing incomplete combustion. And so incomplete combustion means that it does not fully oxidize the carbon. So either there's not enough oxygen present, or the oxygen is not mixed efficiently enough with the fuel for it to burn completely. You can think of this, the best example is probably if you take a Bunsen burner. When you open up the valve at the bottom of a Bunsen burner and it burns with a very sharp blue cone, that is the complete combustion of the methane fuel. It's specially designed to pull in the oxygen and mix it with the fuel so that when it burns completely and it burns hottest. However, if you close off that valve and you prevent the oxygen from mixing with the natural gas, the flame becomes sort of yellow, it becomes wavy, and it will leave a lot of soot behind on anything that is over it. And so that's an example of incomplete combustion. And during incomplete combustion, the carbons, instead of turning into carbon dioxide, although they will still obviously form some carbon dioxide, the other products that get formed are carbon monoxide, which is a colorless, odorless, toxic gas. And they also form solid carbon, which is soot or smoke. And so incomplete combustion produces less heat because you're forming less bonds to oxygen. And it's also dangerous because you're making toxic gases and creating smoke, which you might breathe in and could cause breathing problems. No matter if you burn something completely or incompletely, if the fuel contains hydrogen, the hydrogen will get converted into water. So hydrogens tend to be on the outside of the fuel molecules. And so if the molecules are reacting with oxygen, then the hydrogen atoms will get converted into water molecules. It's not actually the oxidation of hydrogen. If you put in the oxidation states, there's no redox change happening to the hydrogen, but it will convert to water. While we're on the topic of combustion, I think it's important to bring up the topic of acid deposition. Acid deposition is part of the acid-base topic, and it is any sort of wet and dry process by which acidic substances leave the atmosphere. The most well-known by far is acid rain. So if you have rain that has a pH below 5, which is a normal rain has a pH of around 5.6. So if you have more acidic rain than that, then you could classify it as acid rain. But there's also acid snow, acid fog. There can be solid particles like from smoke and soot that are acidic that can also directly deposit onto things and then cause acid reactions to happen with them. Now, the way that acid deposition generally forms is that when certain nonmetals, especially sulfur and nitrogen, if they are present in fuels or if they get mixed with fuels, during the combustion, they can become oxidized when the fuel is combusting. And that leads to the production of sulfur oxides and nitrogen oxides, both of which are gases, which means that as they are formed, they can spread throughout the atmosphere, even far away from where those gases were created, which is not good. And it takes a local problem and makes it spread. But they are also non-metal oxides, which, as we covered previously in the period 3 oxides, means they are acidic when they combine with water. So sulfur is mainly a problem in coal. Coal tends to have a lot of sulfur as an impurity in it. And while you can remove the sulfur, it's difficult to remove all of it, and it's not always done. So if you burn coal, which is mostly carbon, and it has sulfur in it, the sulfur will get oxidized as well, and that will lead to sulfur dioxide gas. And that sulfur dioxide gas can also become further oxidized into sulfur trioxide, according to this equation here. Both of those gases react with water to produce acids. And the one acid here you're supposed to really know is sulfuric acid on the bottom. That's a strong acid. And the one up here is called sulfurous acid, not as strong an acid, but still an acidic substance. So sulfur oxides react with water to produce acids, and that's one of the causes of acid rain, acid deposition. Nitrogen is the major component of Earth's atmosphere, about 78% of the atmosphere. And as gasoline or petrol is combusted inside of a car's internal combustion engine, there's constantly air being pulled into the engine to carry out the combustion reaction. But oxygen gets pulled in, but also nitrogen. And so sometimes when the temperature gets very high, the nitrogen in there can actually combust as well. So the nitrogen can get oxidized into nitrogen monoxide. It can get oxidized into nitrogen dioxide, or the nitrogen monoxide can be oxidized further into nitrogen dioxide. And these gases are also acidic. They will combine with water. There's a couple of different equations you can try to remember for how that happens. But they will combine with water to create acids as well. So the one I try to remember is the top one, that two NO2s combine with water to make actually a combination of acids, one of which you're expected to know by name as nitric acid. And then its slightly weaker cousin, which is nitrous acid. So you are expected to know these equations for how the oxides form, and also equations for how they react with water and the acids that they produce. There are many effects of acid rain which are very bad, like they can have effects on man-made structures, things made out of metal or limestone. They can leach bad ions into bodies of water and affect aquatic life, or they can leach important minerals out of the soil. And they can have direct negative impacts on human and animal life. And we'll deal with more of that in the acid-base topic. But as we talk about combustion, you should know that more than just carbon and hydrogen can be combusted. And when some of those other elements are combusted, they can lead to problems for the environment. The main focus of this video, however, is to look at the combustion reactions and to note a very important mole ratio that exists within them. So I'm going to skip ahead to these hydrocarbons. Methane is the main thing in natural gas. And if we're going to do the combustion reaction, we're going to combine it with oxygen and make CO2 and water. So methane requires 2 oxygens, and it makes 1 CO2, and it makes 2 waters. Ethine is another thing. It's used in torches, and we're also going to combine it with oxygen to make CO2 and water. As we balance it, there are 2 carbons, so we're going to need 2 CO2s. There are 2 hydrogens, so just 1 water. And then as we go through, we're going to see we have an odd number of oxygens. We could use fractions at this point, but why don't we use fractions? We've got 4 oxygens here, and we've got a 5th there, so I've got 5 total. So that means I'm going to do 5 halves O2. I know that kind of goes against what you learned originally about balancing equations, but if we consider these coefficients and reactions as representing moles, then it's no problem to have 5 halves moles of oxygens, or 2.5 moles of oxygen. Just a couple more here. Here is butane, which is used in a lot of lighters. And so we get 4 here. The 10 hydrogens leads to 5 waters. Again, I've got an odd number of oxygens, so I've got 8 here, plus 5 is 13. So to get 13, I simply do 13 divided by 2, because then times 2 will give me the 13 O's I need. And here's one more. This is ethanol, so alcohol lighting on fire. I've got 2 carbons, so I'm going to put 2 here, I've got a total of 6 hydrogens, so I'm going to put a 3 here. And then if I count them up, I've got 4, and I've got 3, that's 7 O's. There's 1 O in the ethanol, so I just need 6 more O's, which is times 3. So those are a whole bunch of combustion equations, and given the starting material, you should be able to write and balance a combustion equation for any of them. And if all you were doing was balancing the equation, you would be welcome to not use the fractions and to double all the coefficients that I've used in ones like the ones for ethine and butane. But what I'm hoping to point out right now is that every time you do a combustion reaction, there's always a special relationship between the moles of carbon and the moles of carbon dioxide. In methane, there's 1 carbon in the methane, and we made 1 CO2. In ethine, there were 2 moles of carbon inside the ethine, and we made 2 moles of carbon dioxide. I think you see where I'm going with this. In butane, there are 4 carbons, and we made 4 CO2s. And in ethanol, there were 2 carbons, and we made 2 CO2s. So when you combust something containing carbon, the moles of carbon always end up having a 1-to-1 ratio with the moles of CO2. They sort of have to, because there's 1 carbon in every CO2, so however many carbons you had in the original molecule, that's how many CO2 molecules you must make on the other side to be balanced. So 1 carbon for every 1 CO2. There's also an important relationship between hydrogen and water. If you look at the hydrogen here, it was 2, and here this is only 1. Because in water, there's 2 hydrogens per molecule, so the number of hydrogens always gets divided by 2 to become the number of waters. So again, here there were 4 hydrogens, and then there are 2 waters. 10 hydrogens, and there ends up being 5 waters. 6 hydrogens total, so 3 waters. So the number of hydrogens is always divided by 2 to get the number of waters. So if you say that this is 1, it's going to be a half of a water, or 2 to 1. If you want to do it more like variables, you could say that x, that's not really an x anymore now, is it? Where's my eraser? I don't even know where my eraser is anymore. Well, that's kind of silly. All right, well, sorry about that. We'll do it in a different color. X carbons makes X CO2s, and Y hydrogens makes Y over 2 waters. So those are special mole ratios that will hold true for all complete combustion reactions. It means that if we determine how much CO2 and water we have, we can actually apply these ratios backwards to figure out information about the empirical and molecular formulas of hydrocarbons. So I'll just try to do one example and then wrap up this video. So if you take a hydrocarbon and you combust it completely, and when you analyze the products, you find out how much water and how much carbon dioxide you have, you can then work backwards to figure out the empirical formula of the hydrocarbon, even though you don't have the chemical equation in front of you. Because 3.6 grams of water, the molar mass of water is 18. Again, you should use your units better than I'm doing in this video, but forgive me with the little marker here. That is 0.2 moles of water. Okay, well, the ratio was that the moles of water is always half of the moles of hydrogen. So if I work backwards, there must have been 0.4 moles of hydrogen in the original compound. So that means if I'm trying to come up with my empirical formula, and I know it has C and H in it, in terms of the ratio, I know that there's got to be 0.4 here. Obviously, we'll have to turn it into whole numbers, but based on the amount of water that was made, the amount of hydrogen must be twice that much, because the amount of hydrogen in terms of the coefficient gets halved when it becomes water, which has 2 hydrogens in each. I'm going to do the same thing for the amount of carbon dioxide, which is 8.8, divided by the molar mass of carbon dioxide, which is 44. And I also get 0.2 moles of CO2. Now, the ratio between carbon dioxide and carbon in any complete combustion is 1:1, which means 0.2 moles of carbon. So 0.2 moles of carbon must have been 0.2 moles of carbon because I made 0.2 moles of CO2, and those moles are always 1:1. So by just analyzing the amount of water and the amount of CO2, I can figure out the amount of hydrogen and carbon that I had, and that allows me to get the ratio of carbon to hydrogen. So the empirical formula of this compound is CH2. So again, all I did was convert the grams into moles of water and CO2, and then apply those mole ratios that carbon dioxide and carbon will always be 1:1, and water and hydrogen will always be 1:2. And I let that tell me the ratio of carbon to hydrogen. We'll do more practice with this in class, but knowing that relationship will come up, or can come up, on the IB exam.